Hello and welcome to Talking Papers, the podcast where we talk about papers and let the papers do the talking. Today we will be talking about the paper BACON, Band-Limited Coordinate Networks for Multiscale Scene Representation, published in CVPR 2022. I am happy to host the first author of the paper, David Lindell. Hello, David, and welcome to the podcast.
Hello, and thanks so much for having me. It's great to be here.
Can you introduce yourself?
So I'm David Lindell, and I was a PhD student and postdoc at Stanford University in the computational imaging lab. And I'll be starting a new position in July as an assistant professor in the computer science department at University of Toronto. And so this was one of the last projects I worked on during my postdoc at Stanford, and really excited to be able to talk about it and share it with you.
Excellent. Can you tell us a little bit who are the co-authors of this paper?
So this paper was done in collaboration with other folks at Stanford University. It was myself, Dave Van Veen, JJ Park, as well as my advisor, Gordon Wetzstein, working together on this project.
So in a TLDR kind of format, 2-3 sentences, what is this paper about?
So this paper is about coordinate networks, which are an emerging type of signal representation that learns to map low-dimensional inputs, such as pixel values in an image, to a low-dimensional output, such as the actual pixel value. And this is an emerging topic. There have been many types of coordinate network that have been introduced and used across applications in vision and graphics and beyond. But most such networks are designed to represent signals at a single scale. So they're limited, for example, to representing images at a single scale or resolution. And they have limited interpretability. They're really black boxes, and it's difficult to interpret their behavior, especially if you pass into the network a coordinate that you haven't explicitly trained on. So what happens? What does the network do between the supervised points? So in this paper, we introduce a new type of network architecture that has an analytical Fourier spectrum. In other words, the bandwidth of the network can be explicitly controlled. So this allows using these types of network for multiscale signal representation, and it also affords much more interpretable behavior because the bandwidth of the network is explicitly constrained. So even if you pass an input coordinate to the network between two supervised points, you know that the behavior of what the network can actually do is limited because its Fourier spectrum is constrained, or the bandwidth of the network is constrained, which basically prevents there aren't going to be high frequency oscillations beyond what you would expect between these supervised points. So in summary, this is really a more interpretable, understandable architecture that can also be used for multiscale signal representation.
Okay, so you kind of touched on a lot of points, and I want to chop it up into specific things. So what is the problem that this specific paper is addressing? So you were talking about these coordinate networks. We know many of them by now. Some call them implicit neural representations or neural fields, right? So what is the problem that this paper is addressing?
So again, we're really trying to make coordinate networks, also known as, there are a few different names, implicit representations or neural fields, for example, more interpretable, and also give them the capability to represent signals at multiple scales. That's really the problem. So if you were to take, for example, say you were to use another off-the-shelf representation that's popular, such as sinusoidal representations or siren or Fourier features networks. And again, these are different classes of coordinate networks that will map input coordinate to an output signal value. Say you're using these to represent an image, in which case you'd pass in image pixel location. It would give you the pixel value at the output. And so you fit the image at a resolution, at a megapixel resolution, so 1,000 by 1,000 pixels, and you train on every single pixel coordinate in that grid. Well, the resolution of that image then is kind of baked into the neural network. So now say you want to extract a low resolution image from that representation, from the siren or the Fourier features network that you've trained, and you query the network on a grid of 100 by 100 points instead of a grid of 1,000 by 1,000 points. So you've downsampled the image essentially by a factor of 10. Well, unfortunately, the representation has baked in those high frequency details from the high resolution image. And if you simply query it on the low resolution grid, you'll see aliasing in the output because that representation, your sample rate is not supporting is not high enough to capture the high frequency details that are in the resolution that's baked into the representation. So these representations are really kind of baked into a single scale or hardwired for that, and they're not scale aware. So you'll see things like aliasing if you simply naively downsample them. So that's the first point, is they're not scale aware. And the second point that I mentioned is, again, this idea of interpretability. So if we go back to this image example, you've trained it on this grid of 1,000 by 1,000 points. So your training set could be, for example, 1 million points. What happens if you super sample the image? So instead of sampling on a grid of 1,000 by 1,000 points, you sample it on a grid of 4,000 by 4,000 points or 10,000 by 10,000 points. Now you're querying the network in between the supervised coordinates. So you can think of this as like a test data set maybe. And you're looking at how the network interpolates between these supervised points. And it's hard to understand what a network like Siren or Fourier features will do, because there's no way to explicitly analyze their Fourier spectrum or their bandwidth. The behavior's not easy to understand. So what we see if you do this is that they'll often have these high frequency oscillations between the supervised points and won't smoothly interpolate. What we're doing addresses this because the architecture we're proposing has an analytical bandwidth. So you can actually constrain the maximum frequency of this network. And so if you were to interpolate between two supervised points, you know that the oscillations won't exceed a given frequency. And so in this way, you can have some guarantees with the representation and understand what it's going to do, even if you don't explicitly supervise on all possible coordinates. Because the bandwidth is constrained, it has this analytical Fourier spectrum. And I think we'll get into that a little bit later.
What is the contribution of this paper?
Yeah, so the contribution is to introduce a new type of neural network architecture that has an analytical Fourier spectrum. And this allows us to do things like multiscale signal representation, and it gives an interpretable architecture with an explicitly controllable bandwidth.
Excellent. Okay, so before we dive into the details of the method, let's talk a little bit about their related work. So which one or two papers should anyone coming to read this paper should read first? So
of course, there's a large body of related work, a lot of work on coordinate-based networks. I think there are some seminal papers to look at which introduce neural representations, propose a few architectures that have been used now quite a lot in the literature. So, for example, sinusoidal representation networks or Siren, Fourier features networks. These, I think, by now are maybe viewed as conventional neural representation architectures. And most papers in this category, papers that use these architectures or build off of them, are essentially using multi-layer perceptron style architectures. So basically, the architecture of the neural representation is linear layers composed together with nonlinearities. And then maybe you have a positional encoding, or you modulate the input coordinates somehow at the very beginning of the network. What we're doing is different. We're not using multi-layer perceptrons. We're using a different architecture based on a recent paper published in 2021 in iClear called Multiplicative Filter Networks. And this is by a group out of CMU. The difference here is that rather than composing these linear layers and nonlinearities together, you're combining the layers not through composition of functions, but through Hadamard product. I think we'll get into the details of that in a bit, but it's a different architecture. So definitely you'd want to read up on Siren and Fourier features, and then also this multiplicative filter networks paper to understand the architecture that we're building off of. And I just want to mention one more paper that is also important, and that is MIP-NERF, which, in addition to extending NERF to multiple scales, actually provides an architecture that could be used as a general purpose multiscale signal representation. But the paradigm here is slightly different. So MIP-NERF basically takes, if I were to kind of paraphrase, basically takes Fourier features networks and introduces another input parameter to the positional encoding that allows you to adjust the scale. So now you can train this network on a data set that has, for example, could be images at multiple scales, and you provide as input to the network the pixel coordinates as well as the scale. And after training across multiple scales, it learns to represent that signal across the space of scales. What we're doing is actually trying to explicitly constrain the architecture so that by design, it can only represent a signal up to a certain bandwidth. So there's a slightly different paradigm here of learning the multiple scales versus an inductive bias in the network that constrains it to a specific scale.
Yeah, I think the first few papers that you mentioned, it's important to understand the whole pipeline, right? It's these coordinate networks. Their input is basically a point in 3D space or a pixel indices for images. And then the output is then either like a signed distance function for 3D or a pixel color for images, right? So, and that's the way it's trained, right? You get a coordinate, you supervise it with the pixel color or the point's distance. And usually the architecture is, it's like you said, either an MLP, like stacked layers, and the activation can change. It can be a ReLU, a soft plus, or a sinusoidal activation, which works great. But in your case, you did something a little bit different. And I think it's time that we start talking about that. So we're moving on to the approach section. So tell us, how did you do it?
Yeah, so I think first maybe I can review a bit how these multiplicative filter networks work, because we're really building off of that work. And maybe now we can get a bit more specific about the inputs and outputs. So let's say that we're training these networks to represent an image. The input to the network would be two numbers, which define the XY coordinates of the pixel location. Oftentimes, we normalize these input values between -1 and 1 or -0.5 and 0.5. And so the image would extend then in the horizontal and vertical dimensions between -0.5 and 0.5. And then by querying the pixel location, the network should output the pixel value at that point. Okay, like I said, these networks, multiplicative filter networks, are slightly different than conventional multi-layer perceptron architectures. So the input to the network is the coordinate, again, two numbers, and we actually have multiple input layers to this architecture. So in each input layer, the input coordinate goes through a linear layer. So there's a matrix multiplication that happens that takes the input dimension from 2 for an image to the hidden layer size. Could be, and this is up to the user or designer to decide. In our case, we used 256 hidden units. So at the output of the linear layer, you have a vector that's 256 elements long. And this goes through a sign activation. So each of these input layers then takes the input coordinate, passes it through a linear layer, and has a sign activation. After the first of these input layers, you have another linear layer, and then you compose it with the next input layer via Hadamard product. So now you have the multiplication of the first input layer after you apply that second linear layer, Hadamard product with the output of your sign activation. Now you apply another linear layer and then have the Hadamard product with the output of another sign activation, and so on and so forth. So the main difference is that rather than kind of composing functions one within the other, like you'd see with the normal multi-layer perceptron, you have this Hadamard product that kind of combines the outputs of all the layers.
So this explains the multiplicative filter networks. Amazing. And yes, so what's the next step? So how do you use that in that multi-scale sense?
So, and I'll also mention, it may be a bit hard to follow the audio description of this. So if you go to the project webpage, I've put together some animations, and the paper, of course, also has a figure. So if you go there, you'll definitely see how all this is working. Okay.
Yes, so all this would be in the episode's description, so it'd be clickable and easy to access for everyone. Okay,
perfect. So what's next? Right. So our main contributions are to actually then look at how you can drive an analytical bandwidth for this architecture and control it. And we also propose an initialization scheme for the network that facilitates this. And one of the key insights that's also shown in the original multiplicative filter network paper is that this Hadamard product between the layers, well, what is it? It's essentially multiplying signs at different frequencies if you write out all the math. And from trigonometry, if you multiply two sines, what does that give you? Well, it gives you, actually, it's equivalent to an addition of two sines at the sum and difference of the frequencies of each sine. So you can look at this multiplicative filter network architecture. You see, essentially, it's a bunch of sines being multiplied together, and you can actually rewrite it or rederive it as a single sum of sines at different amplitudes, frequencies, and phases. So this architecture kind of has this dual nature. In one form, it's written out as I described in this layer-wise fashion, where the layers are combined via Hadamard product. And the other form, you can write it as a single sum of sines, where the number of terms in that sum grows exponentially with the number of layers. And so the more layers you have, the more expressive this network is going to be. And this insight is really useful because if you look at that dual form, the sum of sines formulation, you can actually figure out what the frequencies in the network are. And the network can really only represent signals using those frequencies. And so if you were to actually band limit or limit the extent of those frequencies, limit the highest frequency in the network, you've basically constrained your network to those frequencies. In the paper and in the supplement, we have extended derivations on looking at, well, what are those frequencies? What is the distribution of frequencies? And how can you also initialize the network so that the activations of each layer stay the same distribution and don't vanish? And so that adds some benefit over the original formulation, multiplicative filter network formulation as well, because you can have more layers without the activations going to zero, making these things easier to train.
Let me just pause you there and recap for a second, because this is a really cool thing about this paper. When I read it, I was really amazed by this point, right? So now you're saying instead of this big and long formulation of the layer multiplication, you're basically saying using this simple trigonometric identity, we can put everything together into a single sum where we have these parameters which are interpretable, right, as the frequencies and magnitudes and phase shifts. And that's it. And that's what the network can give us, right? That's really cool. And you can control each and every one of these parameters by band limiting them, right?
Exactly. So that was what kind of drew me into this architecture initially and led me to start thinking about how we can use this. And, you know, it's natural that you see there's such a simple expression for what this network can do. We should be able to use this to help make these types of neural networks more interpretable and more transparent and kind of remove this black box nature. So that's kind of what I was after.
Yeah, amazing. Right. So you want to talk a little bit about the initialization?
So as I mentioned, I think the initialization, I won't get into the specific details of it. Probably that would be best grasped by actually going through the math and looking at the paper. The main idea of that is, again, just to keep the magnitude of the activations consistent as you go through the layer, as is the case with most activations, most initializations. That if you just grab or you think of some random initialization scheme, those layer activations can disappear or go towards zero with deep networks, making them hard to train. So we address that in the paper.
Yeah, so I really like the initialization, like explanation of graphs that you show, that if you don't initialize using the proposed initialization, it actually disappears as the networks become deeper and deeper. And if you use your initialization, it basically maintains the activations throughout the network, kind of independent of the depth.
Yeah, exactly. So this is one technical obstacle that we definitely needed to overcome. But other than that, I mean, you can get into the technical details, but yeah, the gist of it is that it allows you to train deep networks. So at this point, I think we can get into like how we actually use this for multiscale signal representation then, now that we kind of explained the nuts and bolts of what's going on inside. So if you look at this architecture, I said that the number of sines in the representation increases exponentially with the number of layers. And what you'll also see is that the frequency, it's not only the number of sines, but the frequency actually grows from layer to layer. And so you can actually look at the Fourier spectrum at the output of each layer. Like if you looked at the sines that go into each activation function after each layer, and you like plot the Fourier spectrum there, you'll see that it's actually growing outward, which means that you could extract intermediate representations of your signal from these intermediate output layers, and they would have a bandwidth that is differently constrained, or from the first or second output layer, you'd have a very small bandwidth. And then as you move through the network to the last output layers, you'd have a much larger bandwidth. And in fact, you can control that bandwidth and it depends on how you're setting the frequencies in the input layers, or in other words, the frequency values that go into that very first sign activation. So we actually exploit this property in the architecture, and we add an additional linear output layer at these intermediate layers throughout the network. And we train the outputs of these intermediate layers then to represent the signal at different scales. So that's kind of the trick that we use to bring this architecture from a single scale representation to a multi-scale representation, simply adding intermediate linear output layers at these intermediate layers of the network that allows us to take those intermediate activations that are maybe dimension 256, if that's your hidden layer size or hidden unit size, and go to the output dimensionality.
Let me just recap that for a minute. So what you're saying is, instead of the traditional coordinate networks that get a coordinate as input and then supervise it with that single pixel color at a single resolution, using your formulation, you're basically able to extract at intermediate layers these different scale resolutions, right? Different scale resolution images, right? And then you can use different scale images to supervise that architecture, right? So you get a coordinate, that coordinate at one scale and second scale and third scale have a different value, a different color.
Yeah. So you pass in a single input coordinate, and then it would pass through maybe the first couple layers, and then you could extract an output at that point, which would be at the scale given by the bandwidth of the network at that point. So if you wanted a low resolution output, you actually only need to use the first couple layers of the network. So it could be more efficient in that way. If you want the full resolution output, you'd pass the input coordinate through all of the layers, extract the output at the end, which gives you the output with the full bandwidth, and that would give you the high resolution output. Now, the cool thing about this is that when you train it, you can actually supervise it just with the signal at the highest resolution, or the resolution that the highest resolution you need. And you'll actually supervise directly all of those output layers using, could just be mean squared error loss function between the output of the network and the pixel value at each point. And because the low resolution outputs, the outputs with the lower bandwidth, are explicitly constrained, if you try to fit them to that high resolution signal, they'll only fit up to the bandwidth they can. So the network kind of automatically decomposes the signal into these multiple scales simply because that's all it can do. It's explicitly constrained by construction to do so.
Yeah, that's a really cool property of this network. Right, you initialize, you have the Hadamard program, MFNs, you feed that. You only supervise with the high resolution, but if you want, you can supervise with the intermediate ones. That leads us to the results section of the paper. So what experiments did you do?
Yeah, so we had three sets of experiments, three main sets of experiments. We trained the network to represent images. We trained the network for neural rendering in the standard setting, and we trained the network for 3D shape representation. So maybe we can start with the image results, and this is more of a pedagogical example, just to show how the network is working. So in the paper, you'll see that we fitted this image of a lighthouse, and we compared to a few different baselines just for this image fitting example. So we compared to Fourier features, Siren, and then we compared to a version of the MIPNERF architecture where we've adapted this for just image fitting. And again, the idea is that we can use this scale parameter input to MIPNERF to not only fit radiance fields, but to fit any signal, in this case images, at different scales. So what you see with these architectures is for Fourier features and Siren, since they're mainly designed to fit signals at a single scale, if you train them at some nominal resolution and then you subsample the network or you downsample the network, sample the network at a lower resolution, these representations will have aliasing because the resolution of the original image resolution is baked into them. And so if you sample below the Nyquist frequency, you'll see aliasing. For the MIPNERF architecture, or this what they called integrated positional encoding, you actually train this on a data set of images that are scaled to different resolutions. And then it basically learns anti-aliasing. So if you want to extract a representation of the image at a low resolution, you pass in the corresponding scale parameter, and you'll see that the network output is anti-aliased. And then we show the output of Bacon, and we get this output by sampling the output of the network at one of these first output layers that has the low resolution output. And you can see that it's also properly anti-aliased. And it's interesting too to look at the Fourier spectrum of these network outputs. And if you look at the Fourier spectrum for Bacon, you can see that there are actually no frequencies outside of the constrained region of the Fourier spectrum. So it really is essentially performing a low-pass filter on this image. So this is the first case of the image results where we look at what happens when you downsample neural representations. And the second case, we're looking at what happens if you upsample the neural representation, or you sample on a grid that's a finer resolution than what you trained at. And in this case, all the baselines, Fourier features, Siren, as well as MIPNERF, have artifacts in the output because you're sampling between the trained points. This is something that the network hasn't been supervised on. And if you look at the Fourier spectrum, you can see that there are actually these spurious high frequency components that pop up. And so what you get are these rapid oscillations between the supervised points. Whereas in Bacon, if you super sample the network output, or you sample on a higher resolution grid than what it was trained on, and you look at the Fourier spectrum, those Fourier components, the frequencies, the high resolution frequencies actually have a magnitude of 0. So what it's actually doing is equivalent to zero padding in the Fourier domain, where it's basically doing a Fourier domain interpolation between those supervised points. So you get a pretty interpretable behavior, and you don't see these high frequency artifacts at the output. So that's kind of the summary of the image results.
Yeah, I really like those results. You can really see how crisp and clean those images look compared to the other baselines.
Well, let me mention one more thing about this. So this interpolation behavior of Bacon is kind of nice because say you're in an application where you definitely don't want the network to hallucinate additional details or to throw in these spurious frequencies. Say you're doing like a medical image reconstruction. It might be nice to know that the network bandwidth is explicitly constrained in this fashion. Another interesting property of this network is that, and we show this in the paper, well, what happens if you send input coordinates to the network that are outside of the domain that you trained on? So if you train on images with coordinates between minus 0.5 and 0.5, what happens if you pass in a coordinate that's at 0.6, or outside that original input domain? And it turns out that because of the way that we initialize Bacon, and because it's actually a discrete frequency representation, the sum of signs has discrete frequencies. The network output is actually periodic. So you can actually sample this network at any input coordinate, and you'll see basically tiled copies of the image extending out to infinity, which is kind of an interesting property.
Yeah, very interesting. Let's say you want to make something that's infinitely, like you can sample at infinite places. Like you're basically compressing everything down to this like one single network that you can sample wherever you want, and you get a value, and it's periodic. I really like you have an example there of this kind of is that a knitted like fabric kind of example? Or
yeah, there's this tileable texture. So if you have a square texture, and if you tile it out at the seams, they come together in a kind of seamless fashion. So we train on one of these tiles, and then if you query the network out to infinity, you just see a repeated texture like this. So it's kind of cool that it can kind of represent these textures out to infinity across the input domain.
Yeah, very interesting property.
Yeah, so let's move on to neural radiance fields. So again, we compared to NERF, the original NERF architecture, as well as MIPNERF for multiscale signal representation. In this case, we're training on a multi-view data set of 2D images, and these images have also been resized to different scales. And again, in this case, we do explicitly train Bacon on the images at each scale, just so that we have an apples to apples comparison with the methods, so that we can calculate the PSNR metrics, for example, on the same images, and we know that the outputs of Bacon are matched to these images exactly. So the trend here is that Bacon does outperform the original NeRF architecture for representing images across these multiple scales. And that's because if you simply train the original NeRF architecture, it not being scale aware, it ends up learning kind of an average across all the input scales that it's seen. So the high resolution scale is kind of blurry. It doesn't accurately represent the low resolution scale, whereas we do much better with Bacon. Still, we see that the MIP-NeRF architecture actually achieves the best performance, and we attribute this to a few things. One reason is likely that it has an additional mechanism in the architecture that accounts for the integration over a larger area as you march along the ray in depth. So it correctly handles this, whereas we're using the simple ray marching and integration scheme in Bacon along a single ray. But one other benefit of Bacon is that if you want a low resolution output, you do only have to evaluate the first couple layers of the network, whereas in the conventional NeRF or MIP-NeRF architecture, you need to evaluate the whole network for all output scales, even if you just want to extract a low resolution output.
This is something that I really liked about the paper. In today's research ecosystem, it's like this amazing race to only show good results and bold numbers, and our method beats everyone else. And I think the fact that you're like showing that MIP-NeRF is actually, in some senses, works better, and took the time and space in the paper to explain why that is happening, I think that's really cool. And it doesn't take away any of the novelty of this paper. Like the whole approach is really novel. And yeah, the fact that there's some other approach that does well on the specific task is fine.
Yeah, and there's a trade-off here, and I think it's also good to recognize that this is some of the first work that's exploring and building off these multiplicative filter networks, and I think there's room for improvement here. Whereas MLP architectures have been more thoroughly explored, and there's been an explosion of work for NeRF, especially exploring these types of architectures. So. Definitely room for improvement, and hopefully other people are interested in this direction, and we can push things further as well.
So do you want to talk about the 3D section of the results?
Yeah, let me just briefly summarize the trends here. So in this experiment, we took a few different shapes represented by meshes, and we converted them to a signed distance function, and we trained the network to learn these signed distance functions to represent 3D shapes. And the performance of Bacon is actually comparable to other representations like Fourier features or Siren. We get about the same fidelity of shape representation. And it's also comparable to recent multiscale architectures like neural geometric level of detail, where you get multiscale outputs or multiscale shape representation. But we noticed that the outputs of Bacon at these different scales are actually much more interpretable and smoother. Basically, what you get is a band-limited signed distance function or low-pass filtered signed distance function at each of these output scales. Whereas with something like neural geometric level of detail, where you are basically representing the shape with features at different scales, at the low resolution scales, you get very sharp and angular representations, probably because of the ReLU nonlinearity they use, but they aren't necessarily band limited in the same way. So here we think that Bacon affords a more interpretable output, where you can really understand what the network is doing to produce the low resolution shape.
Yeah, and since I come from the 3D domain mainly, I find this property really interesting because there's a lot of works on triangle meshes that try to do, simplification or multi-resolution and all of these kind of things, where here it's kind of baked into the network already, right? You get those different band limited outputs, and then you can choose which one to use for whatever application you have next in the pipeline.
Yeah, absolutely.
So I think this feature is like another place of potential for future work as well.
Yeah, so instead of having to run Laplacian smoothing on your mesh, if you represent things as a signed distance function, you can actually kind of explicitly constrain the frequencies in that function based on this the architecture of this representation. And we showed a few other benefits, maybe that I'll mention, in terms of rendering out from this representation. Since you have the signal represented at different scales, when you go to apply a technique like marching cubes to extract the shape from a signed distance function, you can actually do so by evaluating the network at fewer points. So you can kind of start by evaluating the network at the coarse scale, figure out where the empty space is in the representation, and refine the output mesh using marching cubes at the fine scale with just the fine resolution outputs of the network. So we show that you can use this multi-scale surface extraction technique in a more efficient manner with Bacon, because it is a multi-scale representation.
Yeah, I remember seeing this section of the paper and thinking, this could have been a paper on its own. Like, how do you like to do this efficiently and, get like a much faster marching cubes approach? But yeah, that was like, I think it's a very short part right up at the end. And it was like, oh, wait, that's a cool trick. Good thinking.
Yeah. Unfortunately, it's very condensed just because we're so limited in the space. There are more details in the supplement, but we wanted just to show another additional application of this architecture that we thought could be really useful.
Was there anything unexpected that you encountered during the experiments? Maybe some fail cases or something like that?
Well, maybe I can just, when you start research projects, I think many of us have this grand vision for how things would go. And for multiplicative filter networks and this analytical Fourier spectrum, I was really excited about this sum of signs representation. And I was thinking there would be all sorts of really efficient ways to evaluate the network, maybe using like a fast Fourier transform or something like this. And this could lead to much faster methods for neural rendering as well. And so the project actually didn't go in that direction because I couldn't figure out how to go from the layered representation to the sum of signs representation and back and forth efficiently. So there was, kind of a moment where I needed to focus the project, and then I turned towards like this idea of multiscale representation, which I think is a big limitation in the literature. But so that was one unexpected thing. I think happens a lot in research. You have one idea or one vision for the project, and you end up going a different way. So I just wanted to highlight that.
That is research.
Yeah.
I think most of my papers started off like that. I had one idea, and then it kind of took a left turn at Albuquerque.
Yeah. And so that's just what happens sometimes.
Let's move on to the conclusions and future work section. So how do you see the impact of the paper going forward? Have there been any follow-up papers since then?
Yeah, so I hope people will look into this architecture, especially if they want a bit more control over what the network is doing. For example, at the unsupervised points, if they're looking for something that gives them explicit control over multi-scale outputs. And there has been some follow-up work. So I want to mention one concurrent work that's called FlexConv that looks at multiplicative filter networks and using Gabor filters for constraining the bandwidth of convolutional kernels. So this is some really interesting work that takes a similar idea and applies it to CNNs. And I also have some follow-up work with collaborators at University of Toronto on residual multiplicative filter networks. And the idea here is to actually put in residual connections to this architecture, which allows you to grow the frequencies from layer to layer in a more efficient and interpretable way. And we apply it there to cryo-electron microscopy reconstruction, where techniques that reconstruct signals in a multiscale fashion or that do coarse to fine reconstruction is really important. And so this work kind of brings coarse to fine reconstruction techniques to coordinate networks or implicit representations. So again, that's residual multiplicative filter networks. And I encourage folks to have a look at that. And it's up on arXiv.
Cool. Definitely check that out. I'll make sure to put a link in the description to that as well. Moving on to my favorite part of the podcast. What did reviewer 2 say? Please share some insightful comments that you got in the review process and how that made the paper better. Yeah,
so we got a lot of great feedback from the review process. It was a good experience. And so one item of feedback that I think was really good to think about, and reviewers highlighted one of the limitations of Bacon, which is that you have these discrete output scales, right? So it's not a continuous scale representation. And this is absolutely true. Now, one way that you could try to make the output scales perhaps more continuous is to actually just interpolate between the outputs, similar to what's done in MIP mapping in computer graphics. Although this doesn't actually continuously grow the frequencies in the representation, rather it's interpolating between the spectrum of these two outputs. In any case, I think thinking about a way to make continuous scale representations, perhaps using multiplicative filter networks, would be a great avenue for future work as well.
Yeah, it's really interesting to think about how to make that multiscale continuous to any scale, right? Not just selected scales.
Yeah, and I think it's natural because you see the discrete outputs of this representation, and of course you're going to start thinking in that direction too.
Okay, excellent. David, thank you very much for agreeing to be a part of the podcast. And until next time, let your papers do the talking. Thank you for listening. That's it for this episode of Talking Papers. Please subscribe to the podcast feed on your favorite podcast app. All links are available in this episode description and on the Talking Papers website. If you would like to be a guest on the podcast, sponsor it, or just share your thoughts with us, feel free to email talking.papers.podcast@gmail.com. Be sure to tune in every week for the latest episodes. And until then, let your papers do the talking.